I'm good. It's lovely to hear your voice. Mm-hmm. Hey, what happened? What happened? Okay. Really? That's a surprise. A PDF is a screenshot. Mm. Okay. Ryan, share your screen. I would love to see it. I want to know how bad it is. Yes. Nice picture on the background. Is that you who took it? Where is this? I guessed. So the purpose is to show the cars, not the view. I was impressed by the view. Yeah, yeah, I can see.
Okay. The PDF هيك شوي it's flu.
Show me the PDF.
You see the difference?
I'm still waiting. Yeah. Okay, so it's lower quality, but it's still okay, right?
Yeah,
Show me.
it's
Do you
not
have
bad.
do you have worse quality? No, it's okay. I think it's related to the app you're using. So probably
Yes,
other
maybe.
apps, or probably there's somewhere in the preferences where you can increase the quality. I don't know. It's like a screenshot. So a screenshot could have different qualities. But probably this is a good news because you don't have to upload a really big file. I think it reduces the
Yes.
size of the file. And since it's still visible, I would say ignore this effect.
Okay. Here, the thing is, I usually use a website to convert my Word documents, but this time they said the document is the document size is too big, so I used another website.
Okay, what I do is I use Microsoft Word, save as PDF. I don't use any website, any app. I do it through Microsoft Word. I don't know if you can do the same thing.
Yes, it's very simple. You just export it into PDF.
But probably he doesn't have this option. Is my Word open? For example, this is for you. I do file save as or export, but I don't use export. So I click save as and I pick PDF. Try it as well.
I didn't know about this option. I'll try.
By the way, I want you to experiment in this. This is not a waste of time. This is good for you because eventually you need to submit your midterm probably or final exam or any other report. Okay, I'm gonna have a quick look over lab 3. I can see everybody submitted lab 3, which means except Maria. I'm gonna talk to Maria. Probably she dropped. I don't know. All right, so what I'm trying to say is I want us to go over a little bit about the bulb. Anybody who'd like to speak up about the functioning of the bulb? Is it an ohmic device or not? And why does it act like an ohmic device sometimes? And why not like an ohmic device all the time? Because 20% of the class is still confused about the skin effect and they don't know how to explain it. And then they discuss frequency versus temperature, and they some students are confused between temperature and period because both are capital T. So I can see some confusion in the air and I would like to give you feedback about it. Anybody would like to speak up? Bulb, ohmic or not, and why frequency changes the resistance? Any thoughts?
Dr. Anna, I saw the correction. I saw the remarks you wrote on my lab report. Anna, honestly, I went to the internet,
Yes.
and what I wrote down is what I found on Google.
I know.
So I found something that was like when the frequency increases, the resistance increases. So
yeah, I still remember yours.
that's what
Probably
I think.
it was the last lab report I corrected today. Yeah. Anybody else would like to say something about this idea? So my question is related to the bulbs. And what I mean by bulbs is how are they, how do they function, ohmic or not? And how does the frequency affect the behavior of the bulb? Anyone? So please unmute and talk. So Jean, yes, you'd rather convert your document to PDF because I don't want your drawings or your graphs to be modified or anything, okay? Now back to the bulb, since nobody wants to speak up, listen up. The bulb depends on temperature. The resistance of the bulb depends on temperature. So the bulb sometimes would heat up. The greater the brightness, the greater the temperature, and the greater the resistance. When the frequency is low, the bulb has enough time to heat up and cool down as it goes on and off. I don't know if you can see my camera. So it will heat up and cool down, and so the resistance increases, then decreases, and you see this butterfly shape due to the change in the slope. When the frequency is high, the bulb will go on and off so quickly, and you cannot see it in the naked eye. It doesn't have enough time to cool down. So the slope is initially low, and then it increases a bit and stays on and high all the time. So it's still temperature dependent. I cannot really see if it's ohmic or not, but I can see that R is constant because it does not have enough time to cool down. So this is why you see this weird effect. Do I make sense?
Yes, doctor.
All right, thank
Can
you,
you repeat,
Dana.
doctor?
Yes, ask Joe, what's wrong?
Can you repeat what you just said?
Okay, so basically the bulb has a resistance, and this resistance is temperature dependent. The greater the brightness, the more hot it becomes, the greater the temperature, the greater the resistance. When the frequency is low, the bulb will go on and off at a very slow pace. So it has enough time to heat up, then cool down, heat up, then cool down. So the resistance increases, then decreases, increases, then decreases. So you will see a change in the resistance, and therefore you can see that the curve is actually looks like a butterfly, you know? When the frequency is high, the bulb goes on and off so quickly you cannot see it in the naked eye. Also, it goes on and off so quickly that it doesn't have time to cool down. So the resistance increases and it stays high all the time. And it shows you this very constant effect. You see what I mean? Constant effect means you would think it's acting like an ohmic device, but it's not. But simply it doesn't have enough time to cool down. That's why you don't see the variation in the R. Do I make sense?
Yes, doctor, understood. So that was the answer for question number 13?
Yeah, or anything close to this. Okay, it was an open answer, but if you can relate frequency to temperature, basically there's no relationship between frequency and temperature, but the fact that it has enough time or not enough time to cool down, that's all. Okay, yes. Now I want us to start with lab 5. I remember saying to my first section that it's my favorite lab. I'm gonna tell you why. So, and probably fetch the video. This is the video. Put it away a bit, okay? And keep your names close to me because I would love to have your names close to me, okay? And move this a bit. RC circuits. I'm gonna put the chat away. I hope I can manage to see everybody's chats. All right, what about lab 5, RC circuits? Why do I like this lab? First of all, the first time we studied RC circuits, I was in grade 11. I was impressed by the charging and the discharging process. This is something you'd never visit in middle school or early in high school. But I never had the chance to observe how the charging process was happening. I know that we are in physics lab at AU. We can simply use sensors and data studio to observe the charging and the discharging process. But when you realize that you can use a simple voltmeter, which can be found in any house, I suppose probably maybe you have a voltmeter at home, you can plug it across a capacitor and you can observe on a digital voltmeter that the voltage is increasing slowly. I never thought I can do that with a voltmeter until I tried it with RC circuits, you know? I thought I need an oscilloscope or probably I need data studio for that. Imagine you can do all this lab using a digital voltmeter. Probably in Beirut, they use it on data studio, but we decided in Biblos to keep it using a voltmeter to show you that it's a process that can be measured using very simple tools. Okay, let me start by explaining what is RC circuit, then how the charging and the discharging process happen, and how do we measure some parameters, and then the lab itself and what you need to do. Okay, it is a very simple lab. You have no data analysis to do, RMS, linear regression, nothing is there, you know. And I know that you want to do the work in teams and groups of 2, but you don't really have to because this lab is actually short, but it's your choice again. Okay, RC circuits, I need someone to define RC circuits. What do I mean when I say RC circuits? Just speak up. RC circuits.
We put a capacitor with a resistor and a battery to charge the capacitor.
Yes, Jana, and Jean is also saying that we need a capacitor. Jana is saying we need a resistor. Probably I can try to type it and insert a text box. So basically you're saying 1, you need a capacitor, 2, you need a resistor. That's the minimum requirement, right? And you need a battery to charge the capacitor, right? Okay. Now I'm going to show you many circuits. I want you to focus on circuit 1 and circuit 2. Definitely you can read, it says charging and discharging a capacitor. I need someone to tell me, why do you believe circuit 1 is charging and why do you believe circuit 2 is discharging?
In circuit 1, we have a power source, a battery. In circuit 2, we don't.
Yeah, it's very simple. We have a battery, so the capacitor charges itself. We don't have a battery, so the capacitor cannot charge itself, and basically it will empty itself. So now imagine this capacitor fully charged. It has a lot of electrical energy inside. Where does it go? Because eventually it discharges itself to 0. Where does the electric energy go? It disappears just like that.
It's dissipated by the resistor as heat.
Exactly, it goes inside the circuit, and every time the current goes through the resistor heats up and gives thermal energy to the environment until we lose all the joules stored inside the capacitor. Okay, so this is a charging circuit, this is a discharging circuit, and this is a very smart circuit. I need anyone to explain to me. By the way, do you see the switch? You can go on position A or position B or anywhere in between. What happens when the switch go on position A or position B? Anyone? Look at the switch.
Which diagram, B or A?
A. What happens when it go on A?
When it's on A, I think it's charging.
Yeah, you can see that whenever the switch is on A. Yes, Jenna, I can read you. So you have a battery.
And B is discharging.
And whenever you are on B, the battery is outside the circuit. Yes, and then you will have some discharging. I don't want to show the direction because we need really to discuss the direction. Probably we can do that now. The battery has a positive terminal. It will induce a positive terminal on the capacitor and negative. Now it's fully charged. Whenever it empties itself, the discharging current will be in this direction. So the charging current is clockwise and the discharging current is counterclockwise. It's always opposite, charging current versus discharging current. By the way, this circuit, circuit 1, is when the switch is on A, and circuit 2 is whenever the switch is on B. So these are not charging and discharging circuits. These are two circuits to summarize what's happening in this one. We are not going to do this in the lab. Experimentally, it's a little bit complicated. We're gonna make our charging circuit, do the experiment, finish, then do the discharging circuit, do the experiment, and finish, okay? Now I'm gonna discuss the charging curves alone. Again, I need someone to remind me, probably Ahad. Hello, Ahad. I've been correcting your lab reports this weekend. I want you to check them out and come back to me if you have a question. Can you talk to me? Probably he's offline. All right, anyone else? Is that a charging or discharging circuit and why? How do you know?
It's clockwise, the direction of the current.
Actually, clockwise and counterclockwise will tell you nothing, Dana, because it depends how it was initially charged.
Yeah, it's because the positive charge is moving towards the capacitor.
Yeah, so the reason why we say this is a charging circuit, it's only because we have a battery. There's no other reason. The battery will make my capacitor being charged. It cannot discharge itself. Current being clockwise or counterclockwise tell me nothing depending on the initial charge of the capacitor. It can simply do anything. Now I need someone to explain the first curve, that is charge versus time. Anyone? I would like to know, why is it increasing? Is it increasing linear or some other shape? I need to discuss the maximum value, the initial value. I want to discuss the timing it takes, and so on and so forth. Anyone willing to discuss the first graph? It's charge versus time. Yeah.
Can I try?
Yes, of course, and do mistakes, no problem.
Okay, so the capacitor obviously has a maximum capacity of, it can charge to a limit.
Okay, maximum charge. Yeah.
Yes, so this is why on top we get constant value 5.
Okay. So that's the maximum value, and we reach a constant value after some time. You cannot go beyond this value because it's limited by the voltage of the battery that is called V in this case. So C times V is the maximum charge, and we cannot go beyond this value. Yes, Ryan, continue.
Okay.
Is it a linear increase?
No, it's not.
So the increase is exponential. This is simply the behavior of a capacitor, because at the beginning you can charge it fast and then the charging is slow, because basically it's a fact on how you're squeezing in the charge. At the beginning it is easier for you to squeeze on the charge on the plates, and then the process becomes more difficult. It's not linear. Yes, we have a differential equation to prove it, and yes, it's an exponential behavior. I'm trying to make sense out of why it's exponential. At the beginning it's fast, at the end it's slow, because there's pressure against you and you need to compress, squeeze in the charges. That's why it's not linear. So it starts from 0 because it was initially empty. Can you discuss a little bit tau? What is tau? Time constant.
Is the half time or no?
It is the half time. By definition, the half time is the time to reach 50%. This is a bit different. It's called the time constant. What is the time constant? Anyone? So the time constant is called tau. Yes, Jean, would you like to speak up? Jean, any problem with your mic? I would like you to speak up. Okay, Jean doesn't want to speak up, but Jean says, and Jana, tau is the time it takes to charge to 67%. All right, tau is the time constant of the circuit. If you take the maximum value of Q, or U being the potential difference, and you multiply this value by 0.63, which is 63%, you get something 3.2 probably. If you find the time needed, yeah, Jean, if you find the time needed for you to reach this voltage, this is tau. So tau is the time needed to reach 63% of the maximum value once you're charging your capacitor. Okay? How do we find time, tau? It's either experimentally using the graph, or we can simply do, okay, I can see, Jean. We can simply do tau is equal to RC. Okay? Now I have to ask a question for anyone. If I remove this battery and put another battery that is stronger, do you think I can make my capacitor charge faster? Yes or no? So a stronger battery would make my capacitor charge faster, yes or no? Not faster. Why? Because it depends on RC and not V. Exactly. So if I have a stronger battery, probably I can squeeze in more charge at the end, but the process will have exactly, Jana, more charge at the end. So Q max is gonna be higher, but it will take me the same time to charge it fully. This is very important because it's a little bit confusing. Now I'm gonna ask, okay, Dana. So if I have a stronger battery,
Doctor?
yes.
So we can squeeze in more charge, but at the same time?
Yes, so let's say it takes me 100 seconds to fully charge my capacitor. It will take me also 100 seconds to fully charge my capacitor, but instead of reaching 10 microcoulombs, I would reach probably 100 microcoulombs. So the capacitor can be more full, but it takes the same time to fully charge, you know? Think of your phone.
Okay, got it, yeah.
Let's say
so it can fill up more than it can.
Yeah, more. Yes, definitely more, because the Q max is C times V, and V is more, so Q max is more. You can think of your phone. Let's say you have a bigger battery, not bigger battery. Let's say the voltage of the mains is not 220 volts. It's probably 440 volts, and this does not exist in any continent. It will take you the same time to charge your battery of the phone, let's say 30 minutes, but probably you will charge it with more charge, that's all. Now, my example was weird. Maybe you're more confused. Just forget about it. I can ask you about it later on. I need someone to explain the current curve, the current versus time. What's that? Anyone? Yalla, I love hearing your voices. By the way, I found a way to go back to campus. I'm gonna write an announcement this evening. Okay, Jana's saying exponential decrease. So you start with maximum current, although the capacitor is empty, and then the current decreases. Why? You're charging the capacitor though. How come you're charging the capacitor and the current decreases? You can think of your phone as well. Anyone? No one? Okay, so I'm gonna say, no, I did not remove the battery yet, Anthony. So I'm still charging. So look, I'm still charging my capacitor. Okay, so Carmen, let me say it. Your capacitor is being charged. Okay, I'm discussing the current, yes. Initially, the capacitor is empty. The current is maximum. When the capacitor is fully charged, the current goes to zero. How can you explain it? Yes, it is the current in the circuit. And yes, the capacitor, when it's fully charged, okay, I love Jana's approach. I want you to see it. Although it's a mathematical approach, and I'm trying my best not to use math. So Jana is saying I is dq over dt. All right, so it's the change in q over change in time. You see that the change here, or the slope, is very high, and then the slope is less, and eventually the slope is 0. So Jana is using the slope idea from this graph to explain why the current is high, then the current is low, then the current is 0. For me, it's very simple. When the capacitor is empty, like any bottle, it's very easy to fill it in. So the flow of water or the flow of charge will be very high at the beginning. And then when it's very close to being full, you need to squeeze in the charge. There's no more space, no more place for those charge. So probably it's more difficult and the flow is less for you to be able to fully charge the capacitor. So the flow as current is high at the beginning and very low at the end. Okay, so we just gave you two reasons to think about. The mathematical reason, I is dq over dt, and another reason to think about the pressure against you. The capacitor is fully charged, so the flow of current is less and less. All right, so that's it for the charging curves. I'm gonna move to the discharging curve, so discharging, and I'm gonna modify those. I need help in the circuit. How do you think I can modify the circuit to make it a discharging circuit? I need help. How can I modify my circuit? Disconnect battery. Thank you so much, Jana. Now I have an open circuit. I have an empty join R and C. Thank you, Jana. So I'm gonna take a wire and join both. Okay, maybe put my wire a bit here. So now the capacitor that was fully charged, this was the positive terminal and negative terminal, will start flowing current in this direction. So current 1 was the initial charging current. Current 2 is the discharging current. You see that I1 and I2 are opposite. One is clockwise, the other is counterclockwise. There's no theory as long as you say they're opposite. So you charge in one direction and you discharge in the opposite. Now I need help with the graphs. How do you believe the Q, charge versus time, would change? How does it change? All right, it decreases. Where does it start from? Q will become exponential decrease. Okay, it starts from 5, the maximum, because I will assume it's initially fully charged, and it will go down probably like this, down to 0. Can you tell me a little bit about tau? So tau for the discharge, what does it mean? It's the time needed to do what during the discharge? Exactly, to reach 37%. What's 37% of 5? Let me try. So my calculator, 5 times 0.37 is 1.85. So if I reach this one, this is 1.85. So here, somewhere here, yeah? So when I have 1.85, I will reach tau or something like that, okay? So now we have a difference. So tau is still the same. It takes the same amount of time to charge and discharge. I'm talking about the same capacitor in the same circuit, but tau would mean the time taken to reach 37% of the maximum value during the discharge, okay? I need someone to explain to me why the current curve is like this, or probably I need to modify something in it. So how do you believe the current curve will become?
It would be increasing from negative.
You mean decreasing from negative in absolute value, right?
Yes, it's decreasing in absolute value.
All right, so the current is very high at the beginning and go to 0 as the capacitor is emptying itself. But since the current flow is opposite, I will simply put -1, -0.8, -0.6, just to say it's opposite direction. Remember, in physics, we don't have negative. Negative means opposite direction, okay? Negative is a mathematical sign, and we're doing physics in here. So you can simply draw the current as such that, like, this is your I and this is your T, and instead of doing the curve from above, you simply do it from below, mirrored. Okay, it's a mirror. Or simply do this and put minuses, okay? Yes, anyone who can explain why the maximum current is V over R, V being the voltage of the battery? So why is the maximum current V over R? Simply Ohm's law, maximum current is maximum voltage over R total. Okay, that's it. There's no other rationale behind it. Yes, that was the initial, yeah.
Why did we do that I over T graph? عملناها absolute value and we kept it mirroring.
Okay, this is only to explain that the current behaves exactly the same in the charge and the discharge. In the charge, at the beginning, it's so high, then it goes to zero. In the discharge, it's also so high, then it goes to zero. The only difference between charge and discharge, basically this is the charge and this is the discharge. The only difference is the direction of the current. One is positive and one is negative, or one is clockwise, the other is counterclockwise. Okay, but it's the same behavior. At the end, the current goes to zero. At the end of the charging, current goes to zero. End of discharge, current goes to zero. Okay?
Okay.
Fine. This is, by the way, is a surprise for some students. All right? Shall we move to something else? This slide shows you a bit more about tau. It shows you that you can find tau by doing the 63% or the 37% for the discharge. Do you remember how long it takes your circuit to be fully charged? Anyone? 5 tau. Okay, so 5 tau will make you reach approximately 99% of the maximum value. Why 99? Because the behavior is asymptotic, and if you try it experimentally, probably you will never reach 100%. So it's gonna be 99.99. I want to ask you something regarding, let me try to zoom in a bit, regarding this circuit. Which graph, the blue, the red, and the black, has a bigger tau? Bigger tau is for which graph? The black one, exactly. So the black one takes more time to reach the maximum, and probably it doesn't have enough time to reach the maximum if you switch off the circuit. The blue takes less time, and you can see RC is 0.05 seconds in this experiment, and RC for the black one is 0.2 seconds. So it takes more time, and therefore it's slower, you know, it takes more time. All right, this is only to make sure you guys got the idea. Now I'm gonna show you a screenshot from the video to show you how I did the experiment. You're gonna watch the video later, but I want to show you the most important stuff. I did not use a battery. You see my battery sockets are empty. Again, I do not trust the batteries. They behave really bad in this experiment. I want to use a power supply. The power supply is connected through the blue and red banana wires on my board. What is the voltage of the power supply? Anyone can tell from the figure? .9 volts. Yes, it is 2.9 volts. Initially, I wanted to keep it 3 volts because 2 batteries would give me 1.5, 1.5 at 3. But for some reason, it keeps on going down to 2.9. But it keeps on being 2.9 throughout the whole experiment. You can see it on the video. I want someone to tell me if this circuit is series or parallel and what's in it. Don't make it a boring session by typing. Talk. You have beautiful voices. Just unmute yourself. Do some noise. It is a series connection. Yes, I have battery in here, wire, capacitor, the blue one, resistor. Okay, so it's a series connection where I have resistor and C, so RC, and the wire to close the circuit. I have a voltmeter connected across the capacitor because I want to observe on the screen of the voltmeter how the charging process is happening. And you can see it beautifully on the video. It starts from 0 and it goes up so fast at the beginning and so slow at the end. Now with my stopwatch, you see 6.19 seconds, 2 decimals. and 3 sig figs, and you can go up to 4 sig figs as the time goes beyond 10 seconds. I'm timing how much it needs from 0 to 63%. What is 63% of 2.9 times 0.63? It's 1.82. Let me say 1.83 volts. So I'm gonna time and see how long it takes from 0 to 1.83 volts using a simple stopwatch. You can use your smartphone as well because it has the same precision as the stopwatch I have, okay? It's a very easy experiment. Every time I need to empty my capacitor, I take a wire. This is a red wire. Don't tell me this is not gonna... I need a pen, please. Hello, pen, please. I cannot take the pen. I think I zoomed in a lot, and this will make my PowerPoint a little bit acting weird. Pen, please. I need a pen, please. What's wrong with my pen? All right, anyway, I can simply explain it. You take a wire and you connect it across the capacitor. So you short circuit the capacitor by doing this. You empty your capacitor and you can see on the voltmeter 0 volt in 1 second, in a fraction of a second. Then you get ready with your stopwatch, you reset it to 0, and you remove this short circuit, start your stopwatch simultaneously, and you see the charging happening slowly. Now I'm gonna move to the discharging process. Do you think I can insert a text box, or my PowerPoint app is not functioning anymore? It happens, the same thing happened with my first session. Let me try. Text box, insert. No, I cannot insert. No problem, but I would love to save it as and keep it for the students who are absent. Anyway, what's the difference between the previous circuit and this circuit? So the question is for you. Parallel? Probably. No battery. Thank you, Jana. So you see the battery is disconnected. What do you mean wires are not connected? By the way, those springs are connected. So I have a closed circuit. You see it? Closed circuit. You can call it parallel. I simply call it closed circuit. I have a battery. I mean a capacitor, a resistor, and a wire to close the circuit. You see? So is this a charging or discharging circuit? It is discharging. And you can see you start from a high value depending on what is your initial value of the voltage, and it decreases to 0. And here I need to time my capacitor to go down from the initial that was 2.9 down to 37%. Okay, I really would love to write something on this slide. Let me see if I can move to another slide. This app is not great. I don't know if I can update it. I cannot move to a new slide. Come on. Yeah, but I cannot even use the cursor. I'm trying to move to a slide. Maybe use my... Okay, let me try to do something. Could it be from the recording? No, it shouldn't happen. Okay, I can move now. Down again. Hello, PowerPoint. Okay, let me try to insert any text box, please, please, please. Or draw. Can I save as? Let me save as and open it again. So let me call it 2, meaning your section, so we can keep it for us. By the way, I still have only 1 slide, so don't worry. We're done. Okay, do you think now I can try to insert a text box? Yes, I can. So this is the charging process, and let me color it in a yellow. Yes, and copy, paste, and write discharge for the next guy. Okay, discharging. So discharging, cool, and move it to this guy. Fine. All right, now you will be required, I'm gonna zoom in, probably it will give me the same problem. Those pictures probably are really huge, that's why I'm having this difficulty. So you will be asked to change C the capacitor into C2. So you will have R1 and C1, then R1 and C2, then you change the resistor, make it bigger, R2 and C1, then R2 and C2, and study how tau will actually change by timing each circuit. Also, you will be required to put C1 and C2 in parallel, just on top of each other, across the voltmeter, or in series, like next to each other. Do the charging process for all the combinations, then do the discharging process for all the combinations. And this is a quick reminder, which is a series connection, which is a parallel connection. Yes, so this one is series or parallel. So this is a series connection, right? And yes, exactly, Jana. And this is a parallel connection. Okay, so instead to find tau, you do R times C total. C total, you find it first, and then you can relate tau in series to tau in parallel to tau for one single capacitor and so on. Let me show you the lab report before you leave, and probably I'm gonna show you the video. Where is it? Probably it's open in here. I'm not gonna play the video. I will simply show you what to expect. You're gonna see how I'm managing the power supply, how I do the connection slowly, how I plug in the voltmeter across the capacitor, how I time, I'm doing the circuit now, how I short circuit my capacitor, how it gives me 0, how I use the stopwatch to time from 0 to 63%, and how I disconnect the battery and do the discharging circuit and time the discharging circuit as well. Okay, how I start from high voltage before I make it discharge. So I'm gonna share the video with you. Now for the manual, let me show you quickly what to expect. So probably you know how small this is. Question 1, fill in the blanks. Question 2, sketch. They want you to sketch the behavior of the voltage versus time for charge and discharge. Don't plot, please sketch, show the shape, use the draw to draw. Probably you can show one value, not more, or 2 maximum. Probably you can find U max, show U max from the video, or the total time from the video. I will give you tau for the charging, tau for the discharge. They will be a bit different. They shouldn't be different though. A bit different due to the fact that you have different sources of errors for different circuits. You can find the average of those to be able to do the discussion. You do the series and the parallel. You answer some questions. How does the decrease or increasing capacitors will affect tau? You will use your data to explain. Never say linear or proportional unless you prove it. And be careful with the explain, okay? And that's it. You see how easy and short the lab is? Only 4 questions. The tables are already done by me. So I think it will take you 20 minutes to finish. You see? So I'm done. That's it, unless you have some questions. By the way, for the students who did not submit lab 4, I know the deadline in this is this evening. Please, when they ever ask you to explain, you're actually describing the brightness, but you're not explaining why it's less bright or more bright. Try to come up with a theoretical explanation, okay? Sometimes the things look so trivial and so easy, and you say in series the brightness is less. Try to dig deep to say why the brightness is less. It's due to what, okay? Because I corrected 3 lab reports so far, lab 4, and I can see some difficulties in the explanation of the why. Yes, for lab 2 and 3, Dana, you would hate me, but I'm correcting each student, like student 1, lab 1, 2, 3, 4, you know? So you're gonna get your grade, Dana, and it's gonna be sudden, like lab 1, 2, 3, 4 in one shot. Probably this is not healthy, but this is the fastest way for you to have all the grades. I'm trying to manage as fast as possible. All right, I think, Dana, I corrected yours. You want me to check, or let's not do that in public? Because probably you don't want to share your grades. You can email me, I can reply whenever I'm done. I don't know if Blackboard sends you a notification whenever you have a grade, and it's not fair for you to keep on checking every time. Just email me, I can reply whenever I'm done from your personal lab reports. And again, group work is allowed now, okay? How do I do it? I correct one. So let's say Jana and Dana are working together. Jana will post a lab report and Dana will post the same lab report, and they will write the names, both names on top. So I'm gonna correct one and give the same grade to both students, but I'm not gonna correct both lab reports because they are similar lab reports. And I can simply write for Dana, check the comments on Jana's lab report. And Jana, please share, screenshot, download, anything you want. By the way, I think you should download all those lab reports whenever you have them ready, graded, for you to keep, you know, with all the comments. Do they download with the comments on, you think? I never tried. All right, this is good, because whenever you are